in this class, a big part of the class goals and of the curriculum is for you to really understand what axioms are, and theorems, and proofs, and how to put together a proof, and how to read and understand a proof. And so on the first page in these notes, we have of axioms and theorems, we have 2 theorems and several definitions and an axiom. Now, axioms are things that are kind of like theorems in that they are statements about properties. But axioms are things that are kind of our building blocks. They are our base building blocks. They're our foundation. So these are the things that we're not going to try and prove, because we know that there exist weird things out there that maybe don't satisfy all of the axioms. But what we want to talk about and learn about and prove things about is things that do satisfy these axioms. So here we have this one axiom, the distance axiom. In mathematicians speak, it's saying something like we have a space with a metric. And so so we have a plane, which is a set of points. It has a distance function that satisfies the distance axiom. And then we say, okay, using this idea of distance, what things can we define and what things can we prove based on those definitions and the distance properties? So we're going to look here at Theorem 1, and I have copied this into a different file where we can kind of change things around and expand them. So here I've found the right page that we're going to work in. And so what we're going to look at is we're going to look at Theorem 1, and in particular we're going to look at Theorem 1a. And I've written out the proof here for you, and we're going to kind of unpack that proof in this video to make sure that you're understanding each of the pieces and how they fit together. And then you're going to do something that's similar to that's going to use some of the same pieces that we used in proving 1a, and you're going to use it to prove Theorem 2. So here we have Theorem 1a, and so I'm going to erase a bunch of stuff for now. So we have just 1a. We are going to prove that if you pick any 2 points in the plane, that the segment from A to B is equal to the segment from B to A. Now, clearly, I'm going to have to use the definition of a segment. So where's my definition of a segment? It's up here. So the definition of a segment is that it's a set of points in the plane that satisfy a particular equation. So what I'm trying to say is I'm trying to say that this set of points in the plane and the segment BA, so let me change that into the segment BA. So I'm just trying to figure out what I'm going to do here. I need to know what the segment AB is, and I need to know what the segment BA is. So how do I change this definition of a segment AB into a definition of a segment BA? Well, A and B are named constants, and I'm going to switch their order. So what I'm going to do to get my new definition is I'm going to take all of the A's and turn them into B's. And then I'm going to take all the things that were B's and turn them into A's. And now I have done a substitution so that I now have a definition of the segment AB and a definition of the segment BA. I'm trying to show that these are equal. These are both sets of points. So that's why I reminded you of this property of point sets, because we're going to use that here in our proof about these two sets of points. So if I want to show that one set is a subset of another set, I need to show that every element in the smaller set is also an element of the larger set. And if I want to show that two sets are the same set, one way I can do that is to show that S is a subset of T. Everything that's in S is in T. And then show that T is a subset of S. Everything in T is also in S. I put this extra line under my subset notation to emphasize that when I say subset, I don't mean proper subset. So every set is a subset of itself. So subset can include being equal. All right, let's unpack this definition. So this proof. So to do this proof, we start off, it says let X be an element of the segment AB. So what that's doing is doing the every element of one of the sets part. So that's this thing. I'm going to name an element of the first set and I'm going to name it X. Then I got to have my definition. What does it mean for X to be an element of that set? Well, it means that it satisfies this property. And so I can write down that property that's true for X. All right, I need to next prove that X is therefore an element of this set over here. And to be an element of this set over here, it has to satisfy this property. So when I look at this, those equations are actually really similar. If I had all of the commutative laws that I needed, this would just be a commutative law thing. So let's see. First, this has an XB and I need a BX. And this has an AX and I need an XA, and this has an AB and I need a BA. Do I know that commutative property? Well, yes, that's called the symmetric property of the distance. So I can use that axiom to switch the orders. So that is this next sentence. By the symmetric property of distance, I can swap, and I can turn AX into XA, and BX into, and XB into BX, and AB into BA. So really what I'm doing, unpacking this some more, is I am saying three things are equal. So I'm saying that AX is equal to XA. So that's my first piece of this equation. And I'm also saying that XB, distance from X to B, is equal to the distance from B to X. And I'm also saying that the distance from A to B is the same as the distance from B to A. And that's using the symmetric property of distance every time. Now, if I take those three equations and I substitute them into this equation, so I've taken this equation and I've substituted XA for AX and BX for XB and BA for AB right there. And after I do that, make that substitution, I get this new equation. And that is almost exactly the same as the equation I want, except that XA and BX are in the other order. But that is the commutative property of addition. Remember that this distance is a real number, and that distance is a real number. And I have the commutative property for real numbers and addition. All right, now, what has to be true in order to say that X is an element of BA? Well, I need that BX plus XA equals BA, and I know that. So now I get to say that X is an element of BA. All right. I'm going to do a little drawing and highlighting here before we go on to the final property, final line. So I use the symmetric property of distance 3 times, and I plug in to the equation from the definition of AB. And when I do that substitution, I get an equation that is almost what I need up here. The commutative property lets me switch these two pieces. And now I have exactly the property that says that something is on the line segment BA. And so I can say that X is in the line segment BA. And that is my set properties. If every element of S is an element of T, then S is a subset of T. If every element of S, if every element of the segment AB is also an element of the segment BA, then AB is a subset of BA. All right. So what I've done here is really typical of what happens when you're thinking about a proof. So this proof that used to be 2 lines long is now 6 lines long because I've unpacked each of those sentences into what each of them means. I have here the word similarly. Similarly, BA is a subset of AB. You can use that word similarly to save you rewriting things. You can only use it when this result, the proof of this result, would be exactly like the thing you just proved, except for changing the letters. So if I just change the letters, change the numbers, change the variables, then I can turn this proof into that proof. And so that's the case where you're allowed to use similarly. And then I've got this property here, therefore AB equals BA, and that comes from this property of sets. If I can say S is a subset of T and T is a subset of S, then they're the same set. If I can say AB is a subset of BA and BA is a subset of AB, then they're the same set. They're the same set. They consist of exactly the same points. All right. So, before I end this video, I want to talk briefly about the 2 first problems that you're going to be doing with proving things. So I'm going to go back to the Axioms and Theorems file, and I'm going to scroll down to where the exercises start. And so right now you know everything you need to know to do these first two problems. So for the first problem, you're trying to prove that A, the endpoint of the segment, is an element of the segment. And the way you prove something is an element of the segment is you prove that it satisfies this equation. All right? So if you could plug A in for X and say AA plus AB equals AB, and that's always true, no matter what A and B are. So if you can explain why that always has to be true when you plug A in for X, then you have proved that A is an element of that set, which is the line's definition of the line segment. Number 2, you are going to prove theorem 2. So in order to come up with a theorem for you to prove that is going to use this same substitution and symmetric property that we used in this proof of 1a, so I want you to have a chance to practice that process of using properties of distance and making substitutions to prove things. In order to put that in here right at the beginning, we are going to jump ahead and look at this concept of order. So this is an idea that we're going to build on next week, but the idea is that if you have points on a line, try again. Can I do this? Okay. If I have points on a line in some order, so I'm thinking of having this situation where I have point A and then point B and then point C and then point D as I travel along a line. I'm going to say the definition for being in an order is going to be that the distances add up. So if when you go from A to D, you are going to naturally go through B and C before you get to D, so that doing this distance plus this distance plus this distance isn't going to take you any longer. You're going to get the same length as going from A to D. Then that's our definition of being points in order. And so your job with theorem 2 is to start off given points with an order, which means that equation is true. Then they also have the opposite order. So your job for proving theorem 2 is going to be, you're going to need to figure out the definition, what it means for points to have order A, B, C, D, and have order D, C, B, A. And so that's going to be this sort of process where you're substituting variables for other variables. And then you're going to start off with 4 points that are in an order A, B, C, D, which means they have this equation is true. And you're going to use things like the symmetric property of distance and maybe the commutative property of addition, and you're going to take this equation and turn it into the equation for going DCBA. All right, and it's going to be short and it's going to be very algebraic, and this is going to be your very similar process to this one.